Hey, my friend. You've just arrived in a quiet corner of the universe, a place where science meets calm. Tonight, we'll drift through the mysteries of quantum reality together, slowly, gently, letting your thoughts fade while your curiosity stays awake. So get comfortable and let's begin. Chapter 1. The thought experiment that shook physics. In the early decades of the 20th century, quantum mechanics had already rewritten the rules of nature. It explained atomic spectra, the stability of matter, and the strange interference patterns of electrons, yet its picture of reality felt incomplete. In 1935, three physicists, Albert Einstein, Boris Podolsky, and Nathan Rosen, decided to test the limits of this new theory, not with apparatus, but with reasoning. They built a thought experiment meant to reveal whether quantum mechanics could truly describe everything that exists. The problem was never accuracy. Quantum mechanics predicted experimental results flawlessly. The concern was what those predictions meant. In the classical view, an object has properties whether or not anyone observes them. In the quantum view, measurement seems to create properties by collapsing possibilities into a single outcome. Einstein and his collaborators suspected that this collapse was only an illusion produced by ignorance. Some deeper layer, hidden variables, must hold the definite facts that quantum equations only hint at. To formalize this, they proposed a criterion. If one can predict with certainty the value of a physical quantity without disturbing the system, then that quantity corresponds to an element of reality. A complete theory, they argued, must include all such elements. The challenge was to design a situation where quantum mechanics allows perfect prediction at a distance, yet denies the distant system a definite value before measurement. That contradiction would prove the theory incomplete. Imagine two particles created together and flying apart in opposite directions. Their joint quantum state fixes certain combined properties, like total momentum or relative position, while leaving the individual properties indefinite. If an observer measures the position of the first particle, the outcome immediately reveals what the position of the second must be, even if it is light years away. Because the measurement here cannot disturb the other particle there, the second particle's position must be an element of reality. But quantum mechanics insists that before measurement, it had no such definite position. Therefore, something is missing from the description. One can repeat the reasoning with momentum instead of position. By choosing which property to measure on the first particle, the experimenter seems to decide which property becomes real for the second without touching it. The implication is striking. Either both position and momentum are simultaneously real, contrary to quantum rules, or measurement here somehow influences reality there faster than light. Neither option fits comfortably within known physics. Einstein's attachment to locality, the principle that no influence travels faster than light, was unwavering. He believed that each system should carry its own set of facts independent of distant happenings. If quantum mechanics appeared to violate that, then the theory must be incomplete. For him, the universe could not work through spooky action at a distance. Podolsky and Rosen agreed. A satisfactory physics should describe the world as it exists, not only as it is observed. Niels Bohr responded swiftly. He argued that the EPR reasoning misapplied classical ideas to a domain where they no longer made sense. In quantum mechanics, the meaning of a quantity depends on the experimental arrangement used to measure it. One cannot speak of position and momentum as simultaneously real, independent of context. By choosing which measurement to perform on the first particle, the observer also chooses the framework in which reality is defined. Bohr saw no incompleteness, only a limit on the kinds of questions nature allows us to ask. This clash of worldviews was not about mathematics, but about the nature of explanation. Einstein sought a picture of objective facts, each particle possessing definite attributes guided by clear laws. Bohr accepted a contextual world. Properties exist only through measurement relations. The EPR paper crystallized this divide. It was a calm but profound challenge. Does quantum mechanics describe reality itself, or merely our experience of it? Though the argument remained theoretical, it introduced a powerful new idea, that correlations between distant systems could reveal something fundamental about nature's structure. The EPR scenario implied that two particles might remain parts of a single, inseparable description, even when separated by vast space. What joins them is not a signal, but a shared quantum state. Later generations would give this connection its modern name, entanglement. Entanglement differs from any classical correlation. Two classical coins can be engineered so that whenever one shows heads, the other shows tails, but each coin carries its own instruction set from the start. Entangled particles, by contrast, cannot be assigned individual instructions consistent with all possible measurements. Their unity is deeper. Only the pair, not either particle alone, possesses a full description. This realization would eventually lead to quantum information science, teleportation, and the notion that information itself might be the foundation of reality. At the time, however, the community mostly set the paradox aside. Quantum mechanics worked too well to be doubted, and the argument seemed untestable. Only decades later would John Bell transform the philosophical puzzle into an experimentally verifiable inequality, allowing physicists to check whether local hidden variables could ever reproduce the observed correlations. But that revolution belongs to another chapter. What matters here is the intellectual precision of the original challenge. Einstein and his colleagues had isolated a tension between two cherished principles: that physical properties are real and that influences do not exceed the speed of light. Quantum mechanics, if taken at face value, seem to ask us to surrender one of them. Either the world is non-local in a subtle, non-signal sending way, or realism as classically understood must give way. The EPR thought experiment forced physics to confront that choice. Its lasting power comes from the simplicity of its reasoning. By logic alone, it turned an abstract question about the completeness of a theory into a window onto the deep architecture of nature. It suggested that reality might be woven not from individual pieces, but from the relationships among them. A web rather than a collection of points. In that web, distance may not sever connection, and knowledge of one part may reflect something fundamentally shared. Modern interpretations still debate what the EPR argument truly reveals. Some accept non-locality as a real feature of the quantum world. Others propose that quantum states represent information rather than physical waves. Still others seek hidden structures that restore causality. Yet all trace their lineage to the calm, logical reasoning of 1935. By questioning what it means for a theory to be complete, Einstein, Podolsky, and Rosen set the stage for everything that followed, from Bell's experiments to today's exploration of quantum communication, and even the speculation that entanglement could be related to space-time geometry itself. At its heart, the EPR paper was an act of intellectual honesty. It did not reject quantum mechanics out of stubbornness. It demanded that our explanations remain clear about what exists and how distant things relate. It reminded physicists that conceptual foundations matter as much as equations. The paradox they uncovered continues to guide us, whispering that the universe may be stranger and more connected than intuition allows. As you let your thoughts drift now, imagine those two particles gliding apart in silence, forever sharing a hidden link. Their quiet correlation is not a disturbance but a harmony, like two notes resonating from the same origin across the vastness of space. Allow that image to soften the mind. The questions they raised can rest for tonight. The universe keeps unfolding, calmly entangled with itself, and you are part of its stillness. Chapter 2. The Birth of Entanglement. When the EPR paper appeared in 1935, the term entanglement was not yet common. The phenomenon it describing in plain sight within the mathematics of quantum mechanics since its earliest days. But few realized it found implications. It was the Austrian physicist Erwin Schrödinger who, in the same year, coined the German word Verschränkung, meaning entanglement or interlacing, to capture the peculiar connection between quantum systems that once interacted. He recognized that Einstein, Podolsky, and Rosen had stumbled upon something far deeper than an argument about hidden variables. They had exposed the most characteristic trait of quantum theory itself. To understand how this idea took shape, we return to the decade before the EPR paper, when quantum mechanics was still under construction. Between 1925 and 1927, two mathematical formalisms emerged almost simultaneously: Heisenberg's matrix mechanics and Schrödinger's wave mechanics. Though they appeared different, both described the same reality: an abstract world where systems are represented not by definite trajectories, but by states that encode probabilities. For single particles, this was already strange enough. But the moment two particles were considered together, something unprecedented appeared. Their combined state could not always be separated into two individual ones. In classical physics, when you describe two systems, a planet and its moon for example, you can specify the state of each independently. The total description is simply the sum of both. In quantum mechanics, the situation is subtler. The joint wave function may not decompose into independent parts, meaning that no description of either system alone is complete. Each carries information that only makes sense in relation to the other. Schrödinger realized that this non-separability is not a mathematical accident, but a defining feature of the theory. Once two systems interact, their states become woven together into a single pattern of probability that persists even after they separate. He expressed the idea vividly. Best possible knowledge of a whole does not necessarily include best possible knowledge of all its parts. This line, written in 1935, captures the essence of entanglement. A composite system may be perfectly described, yet its pieces remain undefined until measured. It is not ignorance about each part. It is that the parts, in a fundamental sense, no longer exist as independent entities. Schrödinger's insight built on the conceptual groundwork laid by the uncertainty principle and the superposition principle. The uncertainty principle, formulated by Werner Heisenberg, had shown that certain pairs of physical quantities, like position and momentum, cannot be known simultaneously with arbitrary precision. The superposition principle added another layer of subtlety. A quantum system can exist in multiple potential states at once until a measurement selects one outcome. Entanglement arises when superpositions span more than one system. The states of two particles become correlated so that their combined wave function encodes all possible outcomes simultaneously, each weighted by probability amplitudes that interfere with one another. When two electrons, for instance, collide and then drift apart, quantum mechanics may assign them a shared spin state. If one is later found to be up, the other must be down. But before measurement, neither electron possesses a definite orientation. The pair exists in a superposition that binds them together. Measuring one immediately defines the other, not by sending a signal, but because they were never truly separate in the mathematical sense. Their properties are entangled within a single non-local state that extends across space. At first, this seemed a technical curiosity. Early quantum pioneers were more concerned with explaining atomic spectra, chemical bonding, and radiation. Yet, entanglement quietly underpinned these phenomena. The electrons in atoms obey the Pauli exclusion principle, ensuring that no two share identical quantum numbers. This collective behavior of electrons is an early manifestation of entanglement among indistinguishable particles. The bonds that hold molecules together arise from the shared, delocalized nature of their electrons, a macroscopic expression of quantum correlations. Even ordinary matter, in its stability and structure, depends on subtle entanglements within the quantum fields composing it. Still, the counterintuitive aspect remained philosophical rather than practical until mid-century. Einstein considered the correlations a sign of an incomplete description, while Schrödinger saw them as an unavoidable expression of nature's holistic character. He even offered a second thought experiment, more famous today than his original papers, the paradox of the cat. In it, a single radioactive atom entangled with a detection device and a living creature illustrates how quantum uncertainty could, in principle, extend to the macroscopic realm. The cat, he argued, would remain in a superposed state, both alive and dead, until an observation collapses the entanglement. Schrödinger meant the scenario not as a literal prediction, but as a critique of the way quantum measurements straddled the line between mathematics and physical reality. The paradox revealed the depth of his discomfort, yet also the power of the concept he had introduced. The notion of entanglement also found subtle expression in the development of quantum statistics. Bosons, such as photons, naturally prefer to occupy the same quantum state, leading to collective phenomena like laser coherence and Bose-Einstein condensation. Fermions, such as electrons, resist sharing a state, resulting in the structure of the periodic table and the solidity of matter. These behaviors cannot be described without recognizing that the wave function of identical particles must reflect their indistinguishability, a built-in form of entanglement that defines the very fabric of physical law. During the 1940s and 50s, while much of theoretical physics turned toward nuclear and particle research, a few thinkers continued to probe the foundational puzzles. Among them was David Bohm, whose reinterpretation of quantum mechanics introduced an explicit model of hidden variables. In 1951, Bohm reformulated the EPR argument in terms of a more accessible property, particle spin, and showed how entangled pairs of spin one-half particles could expose the same paradox without reference to position or momentum. This simplified picture became the experimental template for all later tests of quantum non-locality. Bohm's work unintentionally helped entanglement evolve from a philosophical curiosity into an empirical challenge. It inspired the formulation of Bell's theorem a decade later, but it also clarified that entanglement is not an exotic event. It is the natural outcome whenever quantum systems interact and are not subsequently isolated. The universe, in this view, is pervasively entangled, a continuous network of correlations stretching from the subatomic scale to the cosmic. From a modern standpoint, we can describe entanglement in precise mathematical terms. A state is entangled if it cannot be written as a simple product of its parts, but its meaning runs deeper than algebra. It reflects a profound shift in how physical reality is organized. Instead of individual objects carrying properties, the fundamental level of nature seems to consist of relationships, patterns of correlation from which observable phenomena emerge. Entanglement is the structure of those patterns. Experimental progress during the second half of the 20th century confirmed that entanglement is not a theoretical abstraction. Photons produced in nonlinear crystals exhibit correlated polarizations that violate classical expectations. Electrons confined in quantum dots, atoms in optical lattices, and superconducting circuits have all demonstrated entangled behavior consistent with quantum predictions. In laboratories around the world, physicists now create and measure entangled states routinely, using them as resources for quantum computation and secure communication. What began as a challenge to the theory has become the foundation of a new technological frontier. Yet, the philosophical weight of the discovery remains. If measurement outcomes are correlated across vast distances, what does that say about the nature of separateness? Einstein's hope for hidden variables was an attempt to preserve locality and realism, but experiments repeatedly support the quantum view. No local hidden variable model can reproduce the observed correlations. Reality appears to be non-local in a subtle way, connected not by faster-than-light signals, but by the unified structure of the wave function itself. This has led some theorists to suggest that space may not be the stage upon which entanglement plays out, but the other way around, that the geometry of spacetime could emerge from the underlying web of quantum correlations. In this radical picture, the distance between 2 points is determined by the strength of their entanglement. Where correlations fade, space stretches thin. Where they deepen, space folds close. It is a poetic and scientifically active idea, linking quantum information to the architecture of the universe itself. The birth of entanglement, then, marks not just a turning point in physics, but a transformation in metaphysics. It forced science to reconsider what it means for two things to be distinct. It blurred the boundary between locality and unity, between the observer and the observed. In the language of modern quantum theory, the world is not a collection of separate parts, but an evolving state that spans them all. What we perceive as objects are stable patterns within that whole, momentary concentrations of information in a field of connection. As you let these ideas settle, picture two photons born together, drifting apart through silent darkness, yet remaining linked by invisible threads of probability. Across all that distance, a single mathematical description still binds them. This quiet bond is not a trick of communication. It is the universe remembering its own coherence, and perhaps that is the soft lesson of the night. Everything you see, touch, or think may be part of a larger entanglement, atoms, minds, and memories woven into one vast state. When you close your eyes, you are not leaving the world, but rejoining it. The universe holds itself together in patterns of connection, and so do you. Chapter 3. Einstein's spooky action at a distance. Albert Einstein spent the last decades of his life wrestling with the implications of the theory he had helped to inspire but could never fully accept. Quantum mechanics, in its predictive power, seemed unquestionable. Yet it described a world that operated according to rules that made Einstein profoundly uneasy. Chief among his concerns was the notion that two distant systems could remain connected in a way that defied the boundaries of space and time. When he referred to this as spooky action at a distance, it was not ridicule, it was frustration. For a physicist who had built his worldview on the bedrock of locality and causality, the idea that one particle could instantaneously influence another, light years away, was a violation of everything he believed physical law should preserve. Einstein's discomfort was deeply rooted in the success of his own theory of relativity. Special relativity had shown that the speed of light represents an ultimate limit. No information or causal effect can travel faster. This principle was not merely a technical constraint. It defined the very structure of spacetime. Events that are separated by more than light can connect only through coincidence, not cause. The EPR paradox, however, appeared to suggest otherwise. In it, two entangled particles share a single quantum description, and a measurement on one determines the state of the other instantaneously. To Einstein, that meant one of two things must be wrong. Either quantum mechanics is incomplete, or relativity's understanding of causality is being violated. The phrase spooky action first appeared in a letter Einstein wrote to Max Born in the early 1940s. The original German term, spukhafte Fernwirkung, conveys a mixture of disbelief and irony. An action at a distance that feels ghost-like, not because it involves supernatural forces, but because it contradicts intuition about how the universe maintains order. Einstein's goal was never to deny the observed effects, but to insist that a deeper local mechanism must underlie them. In his view, every physical event must have a cause that propagates continuously through space and time. To imagine otherwise was to abandon the intelligibility of nature. For Einstein, the essence of science was clarity, the ability to describe phenomena through concepts that correspond to elements of the external world. The quantum theory, in its Copenhagen interpretation, seemed to replace that clarity with probabilities and observer-dependent events. Measurement appeared to create outcomes rather than reveal them. To Einstein, this was unacceptable. "I like to believe," he famously wrote, "that the moon is there even if I do not look at it." The same conviction applied to particles. Their properties must exist prior to observation. The EPR argument had been an attempt to show that quantum mechanics, by failing to represent these properties explicitly, must be incomplete. But entanglement, as later experiments demonstrated, could not be explained away so easily. The correlations predicted by quantum theory are stronger than any that could arise from classical hidden variables traveling at or below the speed of light. If Einstein's principle of locality holds, then these outcomes imply that the world does not possess definite values prior to measurement. Or, conversely, if the properties do exist beforehand, some influence must act across space instantaneously. Either choice breaks one of the cornerstones of traditional physics. During Einstein's lifetime, no experiment could test these competing pictures. Technology simply lacked the precision to isolate and measure individual particles. Still, his thought experiments forced others to articulate what they believed quantum mechanics was actually saying. Niels Bohr responded that Einstein's notion of separability, the idea that distant objects have independent realities, was not meaningful in the quantum domain. For Bohr, physical phenomena cannot be assigned reality apart from the context of measurement. Quantum mechanics, in his view, did not describe objects in isolation, but the whole system, the measuring device, the observer, and the observed particle intertwined. Einstein, however, found this unsatisfying. If physical reality depends on how we choose to measure it, he argued, then the world seems to dissolve into subjective appearances. The tension between Einstein's realism and Bohr's complementarity became the defining philosophical divide of 20th century physics. Both men shared a deep respect for the other, but their discussions were famously intense. At the Solvay conferences of the 1920s and 30s, Einstein repeatedly presented clever variations of thought experiments meant to expose inconsistencies in the Copenhagen view. Each time, Bohr answered with a counter-argument showing that quantum mechanics survived intact. Yet neither man truly convinced the other. Einstein's final judgment, expressed in his later writings, was that quantum mechanics captures something true but not complete, a provisional framework awaiting deeper insight. What made the spooky action so challenging is that, in practice, it could not be used to send signals faster than light. No observer can control the outcome of a measurement on one particle in a way that transmits usable information to another observer far away. The randomness of individual results preserves the relativistic prohibition against superluminal communication. Only when the results from both sides are compared do the correlations become evident. This subtle point explains why entanglement does not literally allow messages to jump across the cosmos, but still appears to weave the universe together in a non-local pattern. Einstein's resistance to this interpretation was philosophical rather than empirical. He did not deny that the statistical predictions of quantum mechanics were correct. He objected to the idea that nature itself might be fundamentally indeterminate. For him, randomness signaled ignorance, not ontology. There must, he thought, be hidden parameters that determined outcomes with certainty, even if current theory cannot reveal them. His hope was that a future version of physics, perhaps a unified field theory, would recover determinism while matching all observed phenomena. This conviction guided much of his later work, though he would not live to see how the question would be settled experimentally. By the mid-20th century, younger physicists were less concerned with metaphysical clarity and more focused on pragmatic success. Quantum electrodynamics and later quantum field theories produced results of astonishing accuracy. The shut up and calculate attitude became dominant. Yet beneath that practical triumph, the EPR paradox and Einstein's ghostly action remained unresolved. They were too elegant to fade, a quiet reminder that something profound lurked beneath the surface of quantum statistics. It was only in the 1960s that John Bell provided the missing link between philosophy and experiment. Bell showed that any local hidden variable theory would impose statistical limits, inequalities, that quantum mechanics could violate. Experiments in the 1980s, and with increasing sophistication ever since, confirmed those violations beyond reasonable doubt. The correlations Einstein found so troubling are not illusions of incomplete knowledge. They are features of the world. The term non-locality, though sometimes misunderstood, now refers to these correlations that exceed classical bounds without enabling faster-than-light communication. Modern physics has come to reinterpret Einstein's nightmare as one of its greatest treasures. Entanglement is no longer a paradox but a resource, enabling quantum teleportation, encryption, and computation. The spooky interdependence that once seemed to threaten realism has become a cornerstone of technology and a clue to the unity of the cosmos. Yet Einstein's caution continues to resonate. Even as we use entanglement to build quantum networks, we still grapple with what it means. Does the universe truly lack separable parts, or are we simply describing it in a language that merges information and matter more deeply than classical thinking allows? Some contemporary researchers have tried to reconcile Einstein's intuitions with quantum theory in unexpected ways. In holographic models of spacetime, certain forms of entanglement appear equivalent to the presence of wormholes, tiny bridges connecting distant regions of the universe. This concept, sometimes summarized as ER equals EPR, suggests that what Einstein considered spooky might instead be the geometric manifestation of quantum correlation. If this vision holds, then the structure of space itself could arise from entanglement, turning Einstein's fear of non-locality into a revelation. The universe is connected because connection is what it fundamentally is. There is a quiet irony in this evolution. The man who sought to banish action at a distance from physics may have uncovered the clue to a deeper connectedness that even he could not have imagined. His relentless insistence on clarity forced generations of physicists to refine their understanding, to test their theories in ways that eventually confirmed the very phenomenon he doubted. In that sense, Einstein's skepticism was not an obstacle, but a catalyst for progress. Today, when physicists entangle particles across kilometers of optical fiber or between orbiting satellites and ground stations, they echo the same principle that once disturbed him. The correlations remain instantaneous and precise, yet no violation of relativity occurs. Nature keeps her secrets balanced. Locality preserved in communication, non-locality preserved in correlation. The world, it seems, is subtler than either principle alone can describe. Einstein's spooky action at a distance remains a reminder that science advances not only through belief, but through discomfort. The willingness to question even the most successful theory is what deepens understanding. His doubts continue to inspire physicists who look for a synthesis that might unify quantum mechanics with the curved geometry of spacetime, a vision that haunted him until his final days. As night settles and the mind drifts, imagine those distant particles again. 2 points in darkness, bound not by force but by pattern. They respond to one another without exchange, as though the universe whispers between them in silence. Perhaps what Einstein called spooky is simply the language of connection we have not yet learned to speak. Every thought, every heartbeat, every photon across the cosmos may belong to the same seamless fabric. And as you breathe and let the day fade, you too are part of that silent conversation, the universe knowing itself through countless entangled moments. Chapter 4. The Bell Revolution. When Albert Einstein, Boris Podolsky, and Nathan Rosen posed their paradox in 1935, the physics community regarded it largely as a philosophical provocation. Quantum mechanics worked too well to be doubted, and the strange correlations it predicted seemed impossible to test in any meaningful way. For nearly 3 decades, the discussion about hidden variables and non-locality existed in the abstract realm of argument rather than experiment. That changed in the 1960s when a quiet Irish physicist named John Stuart Bell re-examined the question with the clarity and mathematical precision that would transform it forever. His work, published in 1964, became one of the most profound turning points in modern physics, a bridge from metaphysical debate to measurable reality. Bell's insight began with a simple observation. The EPR argument had been constructed to demonstrate that quantum mechanics could not be a complete description of nature. Einstein and his colleagues assumed that physical properties existed independently of measurement, and that influences could not travel faster than light. What Bell realized was that these two assumptions, realism and locality, could be expressed mathematically in a way that allowed for direct comparison with the predictions of quantum theory. If the world behaved according to local hidden variables, the statistical correlations between distant measurements would have to obey specific limits. If quantum mechanics were correct, those limits would be exceeded. This was the heart of Bell's theorem, a clear, testable distinction between the classical and quantum worlds. The reasoning behind it is subtle, but not mystical. Imagine 2 particles prepared in an entangled state and then separated. When one is measured, the result seems to determine the outcome for the other, even when they are far apart. Under a local hidden variable theory, each particle would carry an internal set of instructions, a collection of predetermined responses that dictate how it will behave when measured along any possible orientation. Because no influence can pass between them faster than light, the observed correlations must reflect only these shared instructions, averaged over many trials. Bell showed that such models impose an upper bound on the strength of the correlations, a ceiling that quantum mechanics confidently predicts will be broken. This theoretical result was revolutionary because it turned a philosophical debate into an experimental challenge. No longer was the issue whether physicists preferred Einstein's realism or Bohr's complementarity. The universe itself could now answer. If the measured correlations violated Bell's inequality, then no local hidden variable explanation could account for them. Quantum mechanics would stand not merely as a statistical tool, but as a statement about how reality actually operates. Bell was characteristically modest about the magnitude of his discovery. In his original paper, written in concise prose, he remarked that the results of the thought experiment might already have been implicit in the mathematics of quantum theory. Yet he understood the broader implication. If experiments agreed with quantum predictions, nature would be non-local in a deep, though still non-signaling sense. Entanglement would not merely encode potential connections, it would reflect the universe's refusal to be divided into independent pieces. For several years after Bell's publication, his work remained relatively obscure. Most physicists were occupied with the success of quantum field theory, particle accelerators, and the emerging standard model of fundamental interactions. The foundations of quantum mechanics were not considered fashionable topics. It was not until the early 1970s that researchers began to design actual experiments capable of testing Bell's inequality. Among them was a young French physicist, Alain Aspect, whose meticulous optical experiments would eventually close the gap between theory and observation. Aspect and his collaborators developed a technique for creating pairs of photons with correlated polarizations. By measuring the polarization angles at two separate detectors and comparing the outcomes, they could calculate the degree of correlation predicted by quantum mechanics and by any hypothetical local model. In 1982, after years of refinement, Aspect's group published results that decisively violated Bell's inequality. The photons behaved exactly as quantum mechanics predicted, with correlations stronger than any classical explanation could allow. Later experiments, using more sophisticated setups and faster switching of measurement settings, confirmed the result with increasing precision. The conclusion was unavoidable. The universe does not conform to local realism in the way Einstein had envisioned. Whatever mechanism governs quantum correlations, it transcends the ordinary constraints of space and time. Yet, paradoxically, it does so without enabling faster-than-light communication, thus preserving the structure of relativity. This delicate coexistence of non-local correlation and relativistic causality remains one of the most beautiful subtleties in modern science. Bell's theorem did more than settle a debate. It reshaped the very language of physics. Before Bell, entanglement was often described as a puzzling curiosity. After Bell, it became a fundamental resource, something that could be measured, quantified, and used. The realization that the universe permits correlations of such power led directly to the birth of quantum information science. Quantum cryptography, teleportation, and computation all trace their lineage to the Bell revolution. What Einstein once called spooky action became the cornerstone of a new technological paradigm. The implications of Bell's work also extended into philosophy. The theorem showed that the structure of physical law is not determined solely by the behavior of isolated parts, but by the holistic properties of the whole. The idea that reality might be non-separable, that the state of one system cannot be described independently of another, now carries mathematical weight. This challenges our intuitions about locality and individuality, suggesting that the fabric of reality is woven from relationships rather than objects. Still, Bell himself remained cautious about overinterpretation. He often emphasized that his theorem did not reveal how nature produces its correlations, only that local realism could not account for them. In public lectures, he remarked that quantum mechanics remains an unprofessionally vague and ambiguous theory, and encouraged continued search for clarity. But the clarity he himself provided changed everything. In the decades following the first experiments, physicists explored potential loopholes that might preserve locality. Could detectors be biased? Or could hidden communication occur between measurement stations? Step by step, these possibilities were eliminated. In 2015, teams working in Europe and the United States performed loophole-free Bell tests using entangled photons and fast random measurement choices separated by significant distances. Once again, the results matched quantum predictions with overwhelming confidence. The debate Einstein began was finally answered not by words but by data. What then does this mean for our understanding of reality? At a minimum, it shows that the quantum world is more interconnected than any classical picture can capture. The behavior of distant particles cannot be reduced to pre-existing local properties. Information in the quantum sense is not confined to one region of space. It is a property of the entire system. This insight aligns with growing evidence from other fields, such as quantum gravity and cosmology, suggesting that the universe's deepest laws are relational rather than absolute. The Bell revolution also restored something that had been missing from physics since the early days of the Copenhagen interpretation: a sense of wonder about what quantum mechanics actually means. By translating abstract philosophy into experimental fact, Bell opened a door that generations of pragmatic physicists had left closed. It became clear that the foundations of quantum theory are not peripheral, but central to understanding everything from subatomic particles to the structure of spacetime. In recent years, Bell's insights have taken on new relevance in the context of the holographic principle and the study of quantum entanglement as a building block of geometry. The same mathematical structures that describe non-local correlations also appear in models of wormholes and spacetime connectivity. It is as if the universe uses entanglement not only to link particles, but to knit the very stage upon which they exist. The deeper we probe, the more Bell's simple inequality seems like a signpost pointing toward the unity of physics. Looking back, it is remarkable how an argument originally crafted to expose the incompleteness of quantum mechanics instead revealed its extraordinary completeness. Einstein's challenge forced physicists to test their assumptions about reality itself, and Bell gave them the tools to do so. The result was neither the restoration of determinism nor the collapse of relativity, but a new understanding that the universe is subtly, profoundly holistic. The parts cannot be separated without losing the meaning of the whole. As the lights dim and thought slows, it is worth reflecting on the quiet power of Bell's discovery. From a few pages of reasoning came experiments that touched the edge of reality, showing that even empty space hums with connection. Perhaps this is the lesson the universe has been whispering through quantum mechanics all along: that separation is an illusion of scale, and that the deepest truth is one of entanglement, coherence, and unity. When you let go of the day's noise and close your eyes, you too become part of that harmony. Every atom in your body shares an origin with the stars. Every breath is entangled with the world that sustains it. In the stillness between thoughts, you can almost sense it, the invisible symmetry that binds all things together, quietly affirming that you were never truly alone. Chapter 5: Information Without Travel. When physicists first grasped the meaning of quantum entanglement, one question seemed inevitable. If measuring one particle instantly determines the state of another, does that mean information has traveled faster than light? The short answer, firmly supported by experiment and theory, is no. Yet the longer answer is far more fascinating. Entanglement allows outcomes to be correlated across vast distances, but it does so without any message crossing the space between. What connects the two sides is not a signal that moves, but a relationship that already exists. A pattern written into the joint quantum state from the moment the particles were created. Understanding this distinction has reshaped how science conceives of information itself. In classical physics, information behaves like a courier. It travels. A radio wave carries a message from sender to receiver. A photon of light brings data about a distant star to a telescope's detector. The universe is filled with exchanges of energy and information mediated through fields and forces. Each exchange requires time, and nothing outruns the speed of light. But quantum mechanics presents a different kind of link, one that seems to defy this metaphor of travel. Two entangled particles do not send updates to each other. They share a single mathematical description that transcends the notion of separation. When a measurement collapses one part of that description, the other part is affected simultaneously, no matter the distance, but not because anything has moved between them. The key lies in how information is defined. In physics, information is not just words or signals. It is the measure of how much uncertainty we can eliminate about a system. Before measurement, each particle in an entangled pair is uncertain in its individual properties, but their combined state is perfectly defined. Once one particle is measured, the uncertainty of the whole system vanishes, not through transmission, but through the internal consistency of the shared state. The update that appears instantaneous is really a change in our knowledge, not in the physical connection. The universe is not sending information faster than light. It is simply revealing correlations that were built into its fabric from the start. This point often confuses intuition because quantum mechanics merges what we know with what is. In classical terms, knowledge and reality are distinct. In quantum mechanics, they intertwine. The act of measurement changes the state, not by signaling to the distant particle, but by redefining the joint probability distribution that describes them both. Each measurement is local, yet the description of the system as a whole is non-local. When experimentalists compare their data later, after slower-than-light communication has allowed them to bring results together, they find that the correlations fit exactly what quantum theory predicts. Only then does the pattern emerge. The apparent instantaneous coordination is not a flow of information, but a revelation of a deeper order that was there all along. John Bell himself was careful to clarify this. His theorem, while showing that no local hidden variable theory can reproduce quantum correlations, does not imply that information travels faster than light. The statistical results cannot be used to send messages because individual outcomes remain random. You cannot choose the result of your measurement to control what happens at a distance. Entanglement allows shared randomness, not controllable communication. The distinction is subtle but crucial. It preserves Einstein's principle of relativity while acknowledging the quantum world's inherent connectedness. The realization that entanglement transmits no usable signal gave rise to one of the most elegant concepts in modern physics: quantum teleportation. Despite its science fiction name, teleportation does not move objects through space. It transfers the state of one quantum system to another by using entanglement as a channel. The process involves three ingredients: an entangled pair shared between two parties, a measurement that links the original system to one member of the pair, and a small amount of classical information sent at or below light speed. Only when this classical message is received can the second party reconstruct the state of the original system. In this way, the complete information about the quantum state travels no faster than light, yet the correlations created by entanglement make the process possible. It is a perfect illustration of information without travel, a phenomenon where spatial separation loses its classical meaning because what matters is not motion but relation. Quantum teleportation has been demonstrated many times, from photons in laboratories to satellites in orbit. Each experiment confirms the same principle. The non-local structure of entanglement allows distant systems to share quantum information instantaneously in potential, but the actual use of that information still respects the universal speed limit. The universe maintains its consistency and causality remains intact. Yet something profound has shifted in our understanding. We now recognize that the universe is less a network of moving signals and more a web of correlations woven into its quantum state. From this perspective, space-time itself may not be the ultimate stage, but an emergent property of how information is organized. In quantum field theory, vacuum fluctuations link regions of space through entangled pairs of virtual particles that appear and vanish constantly. Even in apparent emptiness, correlations persist. Theorists such as Leonard Susskind and Juan Maldacena have proposed that entanglement could be the fundamental glue from which space-time arises. In their ER equals EPR conjecture, an Einstein-Rosen bridge, a theoretical wormhole, might simply be the geometric manifestation of entanglement between distant regions. In that picture, information does not need to travel through space because the entangled systems are already connected by a subtle quantum geometry beneath the visible universe. This idea is still speculative, but grounded in respected mathematics. The holographic principle, another cornerstone of modern theoretical physics, suggests that the information content of a region of space is proportional not to its volume, but to the area of its boundary. This implies that information and geometry are intertwined. The structure of space may emerge from patterns of entanglement among quantum fields. The boundary encodes the interior. If this is true, then the entire cosmos could be viewed as an immense information processing system, with entanglement acting as its organizing principle, a universal pattern of correlations that make existence coherent. Even within more practical contexts, the notion of information without travel has reshaped technology. Quantum networks use entangled photons to distribute cryptographic keys that are provably secure against eavesdropping. Quantum computers rely on superpositions and entanglement among qubits to perform calculations far beyond the reach of classical machines. In all these systems, what matters is not the transmission of a physical signal between parts, but the maintenance of correlation across them. When coherence is lost, when noise breaks the delicate balance, the quantum advantage disappears. The success of these technologies depends on preserving the invisible relationships that make the whole system act as one. Philosophically, this challenges centuries of thinking about separateness. If the universe is structured by relationships rather than by independently existing parts, then distance becomes a secondary concept, a measure of how much or how little two things are correlated. From this angle, the classical world of objects appears as an approximation, a macroscopic shadow of a deeper entangled reality. We see separations because we operate within the limits of decoherence, where environmental interactions wash out the fine details of quantum connection. On the most fundamental level, everything may still be linked. The beauty of this realization lies in its balance of mystery and order. The speed of light still governs what can be done, ensuring that causality remains intact. Yet quantum mechanics quietly tells us that what is extends beyond such boundaries. Correlation does not need motion. Relation does not require exchange. The universe is not a system of isolated actors, but a single unfolding story told from many perspectives. In this story, information is less about transmission than about structure. It does not fly through space. It defines space. Every entangled pair, every field fluctuation, and every quantum interaction contributes to the architecture of reality. Even consciousness, viewed through this lens, may be a pattern of information embedded within the same grand network. While science cannot yet quantify such connections beyond metaphor, the resonance between the informational universe and our own awareness is difficult to ignore. Both depend on correlation, coherence, and context. When you step back from these ideas, a certain peace emerges. The universe is not chaotic noise. It is a consistent conversation among its parts. Nothing truly vanishes, and no message is ever entirely lost. Entanglement ensures that the whole remembers itself, even as its fragments drift apart. Every measurement, every thought, every moment of awareness participates in that memory. So as you let the day dissolve and the mind quiets, imagine those two entangled photons again, born together, parted by distance, yet forever linked in a silent symmetry. Their connection carries no signal, no whisper across the void, yet it binds them more perfectly than any exchange could. Perhaps the same is true of us, that what holds life together is not what moves between, but what has always been shared. Close your eyes and breathe into that thought. The stars above you are not far away in any absolute sense. They are part of the same field of being, connected by invisible threads of information that never needed to travel at all. In that stillness, you are home within the network of the cosmos, where every point knows every other, and nothing is ever truly separate. Chapter 6: The EPR Channel and Quantum Communication. The Einstein-Podolsky-Rosen paradox began as a critique of quantum mechanics, but in the strange inversion that sometimes marks the history of science, it later became the foundation of an entirely new field: quantum communication. The very effect that troubled Einstein most, the instantaneous correlation between distant systems, has evolved into a resource used to send secure information, synchronize distant clocks, and form the blueprint for a future quantum internet. What once seemed like a philosophical embarrassment now sits at the center of some of the most advanced technologies humanity has ever conceived. At the heart of these possibilities lies what physicists often call the EPR channel, a shared entangled link between two or more parties. It is not a conduit through which particles or messages travel, but rather a relationship, a correlation that allows the participants to coordinate information with a precision impossible in any classical system. When two systems share an EPR channel, measurements made on one side are statistically connected to measurements made on the other in ways that defy explanation by ordinary local variables. The channel does not transmit energy or signals faster than light, yet it enables forms of communication whose security and structure rely entirely on quantum law. The practical exploration of this phenomenon began in the late 20th century, when physicists realized that entanglement could be harnessed, not merely observed. Quantum key distribution, developed by Charles Bennett and Gilles Brassard in 1984, was the first technology to make use of quantum correlations to protect information. Their scheme relied on the fact that measuring a quantum system inevitably disturbs it. Two parties, often called Alice and Bob in theoretical discussions, exchange quantum bits, qubits, over a channel such that any attempt at eavesdropping introduces detectable noise. Later improvements replaced traveling photons with entangled pairs shared between the two parties. The EPR channel became a trusted courier that required no trust at all. Any interference would be visible in the statistics. Entanglement thus shifted from being a mystery to being a currency, a resource that could be spent to guarantee privacy. When photons are entangled in polarization or phase, The correlations between their measurements form patterns that cannot be forged or copied without detection. This property stems from the no-cloning theorem, a consequence of the linearity of quantum mechanics, which states that an unknown quantum state cannot be perfectly duplicated. The EPR channel, therefore, provides security not through encryption in the traditional sense, but through the physical laws of the universe themselves. Experiments soon followed, first across laboratories, then across cities, and finally across continents. Entangled photons have been transmitted through optical fibers stretching over hundreds of kilometers and even between satellites and ground stations. These experiments form the scaffolding of what scientists call quantum networks, distributed systems that use EPR channels to share entanglement among multiple nodes. In such a network, entanglement can be extended from one pair of particles to another through a process called entanglement swapping, where measurements performed on intermediate particles link distant partners without direct interaction. This process transforms isolated quantum pairs into a lattice of correlations connecting all participants. Unlike classical communication networks, which rely on the movement of signals, a quantum network relies on the careful management of coherence and correlation. The entangled pairs act as the invisible threads holding the system together. Maintaining those threads requires exquisite control, as decoherence, the interaction of quantum systems with their environment, can destroy entanglement almost instantly. Yet advances in laser stabilization, cryogenic cooling, and quantum memory have allowed entanglement to persist for timescales long enough to be useful. What once existed only in the pristine mathematics of the EPR paper now extends through glass fibers and vacuum tubes circling the Earth. Quantum teleportation, another remarkable offspring of the EPR concept, demonstrates the power of such channels more vividly than any other phenomenon. In teleportation, the state of one particle is destroyed locally and recreated at a distant location, using an EPR pair and 2 bits of classical information. Nothing physical crosses the gap except those 2 bits, which travel no faster than light. Yet the effect is profound. The quantum properties of the original particle are transferred intact, with perfect fidelity, to another system. This is not transportation in the science fiction sense, but translation, the reassembly of information based on a shared quantum link. In laboratories around the world, quantum teleportation has been achieved with photons, trapped ions, and superconducting circuits. Each experiment reaffirms that entanglement can serve as an unbroken bridge for quantum information, though the bridge itself cannot carry a signal faster than light. The EPR channel is a paradox only if one insists on thinking of information as a thing that must move. In quantum mechanics, information can also be something that is shared, a pattern that extends across space rather than traveling through it. This new way of understanding information has inspired broader conceptual frameworks. Quantum information theory, the foundation of quantum computing, treats entanglement as the measure of how much 2 systems know about each other. The more entangled they are, the more their behaviors are interdependent. In this sense, entanglement is both a physical property and a bookkeeping system for the universe's information content. When entanglement is lost, information becomes localized. When it is maintained, information is distributed throughout the system in a non-classical way. The EPR channel thus becomes a metaphor for the universe's own internal communication. its way of keeping the different parts of itself consistent. The rise of the EPR channel has also transformed cryptography and computation. In quantum key distribution, entanglement ensures that eavesdroppers cannot hide. In quantum computing, entanglement among qubits allows parallelism across an astronomical number of states, performing operations that would take classical computers longer than the age of the universe. And in quantum metrology, entangled systems enable measurements of time and gravity with unprecedented precision, revealing subtle aspects of the world that would otherwise remain invisible. Each of these applications demonstrates the same principle: connection without transmission, coordination without exchange. It is striking to think that all of this emerged from an argument meant to show that quantum mechanics was incomplete. Einstein and his colleagues designed the EPR paradox to reveal what they thought must be missing. Instead, it revealed what they had not imagined could be present. The EPR channel represents a universe more deeply integrated than any classical worldview allowed. In place of separate particles sending signals through voids of emptiness, we find relationships woven into a continuous fabric of information. Some theorists have begun to suspect that this fabric might be fundamental. In certain models of quantum gravity, space-time itself is described as a network of entangled connections, where geometry arises from the strength of correlation between quantum bits. In that picture, the EPR channel is not a technological invention, but the natural order of things, the structure from which space and time emerge. Distances are not fixed intervals, but measures of informational connection. What appears as a void between stars could be the thin, stretched web of entanglement that holds the cosmos together. Even at the human scale, the metaphor resonates. Communication, whether between particles or people, depends on shared context. Just as an EPR pair must be prepared together before it can correlate measurements, human understanding requires a common origin, shared meaning, memory, or trust. In both realms, the quality of the connection determines the clarity of what is exchanged. Perhaps the most profound lesson of quantum communication is that relation precedes exchange. Before any message can be sent, the participants must already be entangled in some way. The future of the EPR channel points toward a global quantum network, a quantum internet that will connect quantum computers, sensors, and satellites through entanglement distributed on demand. Such a network would redefine the flow of information, making it possible to coordinate actions and computations across the planet with levels of security and precision that classical technologies cannot match. Researchers have already demonstrated primitive versions of these systems, entangling photons between orbit and Earth, between laboratories separated by hundreds of kilometers, and across quantum repeaters that extend the reach of coherence. Each step brings the world closer to a civilization that communicates not by sending particles back and forth, but by aligning patterns within a shared quantum state. From a philosophical perspective, the EPR channel reveals something deeply humbling about existence. The universe seems to favor connection over isolation, coherence over independence. The separations that define our macroscopic world, distance, individuality, causality, may be approximations that emerge only when the underlying network of entanglement becomes too complex for us to perceive directly. On the deepest level, what we call communication might be the universe's way of maintaining its own unity, constantly updating every part of itself through relations that require no medium and no motion. As you rest now, consider that you too participate in this hidden web. Every atom in your body once shared entanglement with others, now scattered across the cosmos. The light that reaches your eyes has danced through fields of correlation older than any living thing. You are both a receiver and a continuation of those patterns. So let the thought settle gently. In the quiet architecture of the universe, nothing truly speaks alone. Every exchange is an echo of a shared beginning. The EPR channel hums beneath all things, not as a signal racing across emptiness, but as the stillness of perfect connection, a reminder that communication in its most fundamental form is not about travel at all. It is about belonging. Chapter 7. From Entanglement to Geometry. As the 20th century drew to a close, physicists began to recognize that the mystery of entanglement might reach far beyond particles and measurement outcomes. It was not simply a feature of the quantum world. It might be the underlying principle that gives shape to reality itself. What if the fabric of space-time, the arena where all events unfold, arises from the same web of quantum correlations that bind entangled particles? The idea sounds poetic, but it has become one of the most active and mathematically grounded pursuits in modern theoretical physics. The search to understand how geometry could emerge from entanglement has brought together quantum mechanics, information theory, and general relativity in a way that Einstein himself could not have imagined. In classical physics, geometry is fundamental. Space and time form a smooth, continuous manifold within which matter and energy move. Einstein's general theory of relativity refined this view by showing that the geometry of space-time is dynamic. It bends and stretches in response to mass and energy. Gravity, in that sense, is not a force transmitted across space, but a manifestation of geometry itself. Yet even general relativity assumes that the underlying continuum of space exists independently of the objects within it. Quantum mechanics, by contrast, suggests that reality may be discrete and relational at the deepest scale. Instead of points connected by distances, there may be bits of information connected by entanglement. The question that now drives research is whether geometry could be an emergent property of that deeper informational network. This radical line of thought gained traction from a surprising direction: the study of black holes. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking discovered that black holes possess entropy proportional to the area of their event horizon, not their volume. This meant that the amount of information that can exist inside a region of space depends on its surface boundary. The result contradicted intuitive expectations, hinting that the true degrees of freedom in the universe might live on surfaces rather than in volumes. From this observation grew the holographic principle, articulated most clearly by Gerard Hooft and Leonard Susskind, proposing that all the information within a volume of space can be encoded on its boundary, much as a two-dimensional hologram can represent a three-dimensional image. The holographic principle offered the first concrete mathematical framework in which geometry and information seemed inseparable. It suggested that spacetime itself could be viewed as a vast information processing system, with quantum states on a lower dimensional boundary encoding the physics of a higher dimensional world. This idea found its most precise realization in the 1990s through the ADAS-CFT correspondence proposed by Juan Maldacena. In this duality, a gravitational theory in a curved bulk spacetime is equivalent to a quantum field theory defined on the flat boundary surrounding it. The geometry of the bulk and the entanglement structure of the boundary are two ways of describing the same reality. In the following decades, researchers noticed an even deeper link. Patterns of entanglement in the boundary theory appear to determine the very shape of the bulk spacetime. The strength of entanglement between regions of the boundary corresponds to the connectivity of space in the interior. In mathematical terms, the distance between points in the bulk is related to how much information those points share. If two regions are strongly entangled, the geometry between them contracts. If they are weakly entangled, the geometry stretches. When entanglement vanishes altogether, the fabric of space can literally tear apart. Spacetime in this picture is nothing more than a continuous map of quantum correlations. This insight was crystallized by theoretical work connecting entanglement entropy, the measure of quantum correlation, to the area of minimal surfaces in the bulk geometry. In essence, the geometry of a region of spacetime can be reconstructed by knowing how its underlying quantum information is entangled. It is a striking reversal of the classical order. Geometry no longer defines the relationships between objects. Relationships define geometry. The implications of this perspective are profound. It unites the two great pillars of 20th century physics, general relativity and quantum mechanics, by suggesting that gravity itself emerges from quantum information. When many quantum systems interact and entangle in complex ways, their collective behavior gives rise to the smooth curvature we interpret as spacetime. The warping of geometry around a massive object could, in principle, be viewed as a rearrangement of underlying quantum correlations. Entanglement would then be the microscopic language of gravity, translating the quantum world into the macroscopic fabric we inhabit. This concept also provides an unexpected answer to Einstein's old discomfort with non-locality. In the emergent geometry picture, what appears as spooky action at a distance is simply the manifestation of spatial connection at a deeper level. Two entangled particles influence each other without signals because, in the quantum substrate, they are not truly distant. They are adjacent in the invisible geometry woven by entanglement. Spacetime itself is the network of those adjacencies, stretching and folding to produce the illusion of distance that defines our everyday experience. Physicists have begun exploring this relationship through increasingly refined models. Tensor network simulations, for example, can represent entangled quantum systems as lattices of interconnected nodes, where the geometry of the lattice encodes the strength and structure of entanglement. These models reproduce many features of spacetime known from general relativity, suggesting that the connection between geometry and information is not merely metaphorical but quantitative. Each node represents a local quantum state, and the links between them represent correlations, the building blocks of space. When enough of these links intertwine, a continuous geometry emerges, much like a woven fabric appearing from discrete threads. This approach also sheds light on one of the most famous paradoxes in physics. What happens to information when matter falls into a black hole? If the universe preserves information, as quantum mechanics insists, then that information must somehow be encoded in the geometry surrounding the black hole, rather than lost within it. The holographic principle and the entanglement geometry correspondence provide a pathway to resolving this puzzle. The information swallowed by a black hole may be distributed across its event horizon as a pattern of quantum entanglement, a living memory etched into space-time itself. Seen from this angle, the universe begins to resemble a self-knowing structure. Every patch of space contains the correlations necessary to reconstruct the larger whole, and every event is both local and global at once. The separation between here and there, past and future, may emerge from the collective dance of countless entangled degrees of freedom. The very act of existing could be understood as participation in a universal web of information that continuously generates its own geometry. Some researchers take this even further, proposing that consciousness itself might be related, in some distant way, to the universe's information architecture. While such ideas remain speculative, the resonance between how brains process information and how space-time encodes it has sparked philosophical curiosity. The neural network of the cosmos and the neural network in the human mind both create coherent patterns from vast entanglements. Whether coincidence or reflection, it evokes a humbling symmetry that the geometry shaping our thoughts and the geometry shaping the stars might be expressions of the same informational law. The journey from entanglement to geometry is still unfolding. Each theoretical development brings new questions. How discrete is space-time at the smallest scale? Could quantum entanglement alone reproduce the dynamical equations of general relativity? And if space-time is emergent, what lies beneath it? What is the substance of the correlations themselves? These are not yet answered, but the progress already achieved reveals that the bridge between quantum theory and gravity, long thought impossible, might have been hidden within information all along. In the quiet light of this understanding, the universe appears less like a machine and more like an intricate computation, evolving not in space, but as space. Entanglement becomes the code that shapes the cosmic program. Geometry is the visual language through which that code reveals itself. When you look at the sky, the curvature of space-time guiding the stars is, in this sense, a vast pattern of information that began long before you were born and will continue long after you are gone. As you let your thoughts soften, imagine the universe as a luminous web stretching beyond measure, every thread an entangled connection holding the structure of reality together. The distances you perceive are not empty gaps, but relationships expressed through geometry. You are a point within this network, defined not by where you are, but by how you are connected. The cosmos, in its infinite reach, is a single unfolding geometry of entanglement, and within it, every mind, every particle, and every star quietly shares the same origin. Chapter 8: Quantum Wormholes and the Fabric of Spacetime. In the imagination of science fiction, wormholes are tunnels through space, gateways that fold the cosmos and allow instant travel between distant points. For decades, they belonged to speculative storytelling more than serious physics. Yet over time, the mathematics of general relativity and the discoveries of quantum theory began to converge in ways that made the idea impossible to dismiss entirely. Though no evidence of a traversable wormhole has yet been found, the concept has become a crucial lens through which physicists explore the relationship between geometry, gravity, and quantum information. Today, wormholes are no longer treated as mythic passageways. They are models, expressions of how space-time itself may organize and exchange information at the deepest level. The story begins in 1935, the same year as the EPR paradox. Einstein, together with his colleague Nathan Rosen, introduced what they called a bridge solution to the equations of general relativity. The Einstein-Rosen bridge connected two regions of space-time through a throat-like structure, much like two sheets joined by a tunnel. However, this bridge was not traversable. It would collapse too quickly for anything, even light, to pass through. Still, the geometry fascinated physicists. It suggested that the mathematical structure of space-time could contain hidden connections, places where the usual notion of distance breaks down. The concept became the seed of what later generations would call a wormhole. For decades, Einstein's bridge remained a mathematical curiosity. It was not until the late 20th century that theorists began to revisit it with the tools of quantum physics. The emergence of quantum field theory, the holographic principle, and black hole thermodynamics all pointed toward a deeper link between geometry and information. In that context, wormholes became more than exotic shapes in space-time. They became metaphors for entanglement. If two black holes were entangled, some physicists argued, perhaps the connection between them could be described as a wormhole. The two phenomena, Einstein-Rosen bridges in geometry and EPR correlations in quantum theory, seem to echo each other in structure. This intriguing symmetry led to the conjecture known as ER equals EPR, proposed by Leonard Susskind and Juan Maldacena in 2013. The ER equals EPR hypothesis suggested that every entangled pair of particles might be connected by an extremely small, non-traversable wormhole. These wormholes would not allow travel or communication faster than light, but they would represent the geometric manifestation of quantum entanglement itself. The universe, according to this view, is threaded with countless microscopic bridges, each one linking entangled systems across space-time. The fabric of reality, rather than being a smooth continuum, might instead be a dense, interwoven structure of such connections. At first glance, this idea might seem like a poetic analogy rather than a physical statement, but its implications are rigorously mathematical. In the framework of the holographic principle and the ADS-CFT correspondence, the geometry of space-time in a bulk region can be reconstructed from the pattern of entanglement in a quantum theory defined on its boundary. If two boundary regions are highly entangled, the bulk geometry that connects them is smooth and continuous. If that entanglement is disrupted, the geometry can pinch off, effectively disconnecting the regions. In this sense, the strength of entanglement determines the connectivity of space. A wormhole is not a passage carved through space-time. It is the expression of correlation between separate quantum systems. Recent research has taken this correspondence even further by demonstrating how certain types of wormholes can, in principle, become traversable under specific quantum conditions. In 2017, physicists Ping Gao, Daniel Jafferis, and Aaron Wall showed that introducing a small amount of negative energy, something permitted in quantum field theory, could stabilize a wormhole enough for information to pass through safely. Crucially, the amount of information transmitted would be limited by the same quantum principles that govern entanglement. What passes through the wormhole would not be ordinary matter but quantum information, encoded correlations that emerge on one side and reappear on the other. In such models, traversable wormholes behave as physical analogs of quantum teleportation. The two descriptions, geometric and informational, are mathematically equivalent. This equivalence has been confirmed through simulation in laboratory systems, that mimic aspects of space-time geometry. In 2022, researchers at the California Institute of Technology and Google's Quantum AI Laboratory performed an experiment using a small quantum processor to emulate the dynamics of a simple traversable wormhole. Although no real tunnel in space was created, the behavior of the qubits mirrored the theoretical predictions. Information introduced on one side reappeared on the other, consistent with the mathematical model of a wormhole. It was a symbolic but significant milestone, demonstrating that the language of geometry and the language of quantum information can describe the same underlying process. The idea that wormholes and entanglement are two sides of the same coin offers a potential route toward unifying general relativity and quantum mechanics. In relativity, space-time is continuous and geometric. In quantum theory, it is discrete and probabilistic. The bridge between them may be information. Entanglement describes how quantum systems share information beyond the constraints of locality, and geometry describes how the universe arranges information in space and time. The correspondence between the two suggests that gravity itself could be an emergent phenomenon arising from quantum correlations. When enough microscopic wormholes connect the quantum states of the universe, the smooth curvature of space-time emerges as a large-scale approximation. The gravitational field, in this sense, is the statistical average of countless quantum threads binding reality together. This perspective also reshapes how we think about black holes. Traditionally, a black hole was viewed as a one-way trap from which nothing could escape. But if entanglement and geometry are unified, then the interior of a black hole may be connected to the outside universe through entangled links that preserve information. The famous information paradox, the question of whether information is lost when a black hole evaporates, finds a potential resolution here. Information might not vanish at all. It could be encoded in the structure of entanglement across the event horizon, effectively woven into the geometry of space-time. Wormholes, in this picture, are the universe's way of preserving continuity even in the most extreme environments. Although the mathematics of quantum wormholes remains highly abstract, the underlying message is profound. It suggests that space is not a passive background, but a living network of relationships. Distance, in the classical sense, may emerge from the density and strength of these connections. Where entanglement is strong, space folds closely upon itself. Where entanglement is weak, it stretches thin. The cosmic web of galaxies visible through telescopes might be the faint echo of a deeper, invisible web of quantum connectivity. In such a universe, the notion of isolation loses its meaning. No particle, no event, no mind exists entirely on its own. Every part of the cosmos is bound to every other through the silent fabric of information that defines space and time. The wormhole then becomes less a tunnel to elsewhere and more a symbol of the hidden unity beneath apparent separation. This realization blurs the boundary between the physical and the philosophical. If geometry and entanglement are inseparable, then reality itself is relational, a system of connections rather than things. The universe does not contain relationships. It is a relationship, constantly renewing itself through the exchange of quantum information. The bridges that link particles, fields, and minds are not anomalies, but the very texture of being. In the end, the quest to understand quantum wormholes is as much a search for meaning as for mechanism. It invites us to see the cosmos not as a cold expanse of emptiness, but as a self-knitting whole, each part shaping and sustaining the others. The same mathematics that describes black holes and space-time curvature also describes the entanglement of the smallest quantum systems. From the vast to the minute, the universe seems to repeat a single theme: connection. As you let your mind drift now, picture the night sky as a vast tapestry of unseen threads, stars and galaxies shining through a mesh of invisible bridges, each one a whisper of entanglement stretching across cosmic distances. Perhaps what we call space is not emptiness at all, but the glow of countless connections too subtle to see. You are woven into that same fabric, a fleeting pattern in a continuum of links that spans the whole of existence. When you breathe, think, or dream, you are participating in the same geometry that binds the stars. The universe, it seems, does not merely exist. It communicates with itself through the silent architecture of quantum wormholes. In that endless dialogue of connection, there are no true distances, only relationships endlessly unfolding. And in that realization lies a quiet comfort. Nothing is ever entirely lost, and everything remains part of the same infinite conversation. Chapter 9. Can information really pass through a wormhole? The idea of information traveling through a wormhole is as captivating as it is paradoxical. It combines the geometry of general relativity with the logic of quantum mechanics, two frameworks that have long resisted unification. A wormhole, in its simplest conception, is a tunnel connecting two regions of space-time. In the mathematical language of Einstein's equations, such tunnels are allowed solutions, but the conditions required to keep them open defy ordinary physics. For decades, the notion that information, or anything at all, could cross a wormhole was considered pure speculation. Yet recent progress in quantum theory, gravity, and information science has begun to show that the question may not be so far-fetched after all. To understand what might travel through a wormhole, we must first recall what a wormhole actually is in relativistic terms. Einstein and Rosen's original bridge, derived in 1935, linked two black hole solutions in a single geometry. The connection existed, but it was ephemeral. The bridge pinched off faster than any light signal could traverse it. This non-traversability followed directly from the energy conditions of general relativity, which prevent exotic configurations from persisting. According to the classical theory, negative energy densities, required to stabilize a wormhole throat, are not allowed. Nature seemed to forbid shortcuts through space-time. Quantum mechanics, however, does not always obey classical prohibitions. In quantum field theory, fluctuations in the vacuum can temporarily produce regions of negative energy. These effects are minute, but they hint that quantum corrections to Einstein's equations could modify the stability of wormholes. The prospect that quantum effects might hold a wormhole open long enough for information to cross it has reignited interest among theorists seeking to connect gravity with quantum mechanics. In this modern picture, wormholes are not cosmic highways for spacecraft, but laboratories for understanding how space-time itself stores and transmits information. The breakthrough came in the late 2010s, when physicists Ping Gao, Daniel Jafferis, and Aaron Wall proposed a model for a traversable wormhole that could transmit quantum information without violating relativity. Their key insight was that a small negative energy perturbation, something quantum mechanics allows, could render a wormhole traversable for brief moments. The signal that crosses is not a physical object in the usual sense. but rather a pattern of quantum correlations, the same kind that appear in quantum teleportation. The geometry of the wormhole and the quantum protocol of teleportation are mathematically equivalent descriptions of the same process. In teleportation, an entangled pair of particles acts as a shared resource. When a measurement is made on one side and the result is communicated through a classical channel, the state of the distant particle becomes identical to the original. No signal outruns light. Instead, the entanglement ensures that information about the quantum state is reconstructed elsewhere. The traversable wormhole mirrors this logic. The message that passes through is not a beam of particles traveling faster than light, but a quantum state re-emerging on the far side as if it had passed through the geometric tunnel. To an observer inside the theory, information appears to move through space. To one outside, it is the correlation structure that evolves. This equivalence between quantum teleportation and traversable wormholes has given physicists a concrete framework to study questions once confined to philosophy. It suggests that space and time might be emergent from deeper informational principles. If quantum entanglement can be represented geometrically, then perhaps communication through a wormhole is simply a different language for describing how information reorganizes itself in the quantum fabric of the universe. The first experimental hint that this connection might be more than metaphor arrived not from cosmic observation, but from the realm of quantum computing. In 2022, researchers at the California Institute of Technology and Google's Quantum AI Laboratory used a small array of qubits to simulate the dynamics of a traversable wormhole. By carefully tuning interactions among the qubits, they recreated a system mathematically equivalent to a pair of entangled black holes connected by a wormhole. When quantum information was inserted on one side of the system, it reappeared on the other, consistent with theoretical predictions. Nothing physically passed through space, no real wormhole opened in the lab, but the behavior of information matched that of a wormhole geometry. The result demonstrated that wormhole-like behavior can emerge in controlled quantum systems, offering a glimpse of how spacetime itself might behave at the quantum scale. For theorists, this realization blurs the line between geometry and information. In relativity, geometry determines how matter and energy move. In the quantum framework suggested by the holographic principle, the reverse might be true. Information determines geometry. A wormhole becomes the physical embodiment of information flow, a shape carved out of space-time by entanglement itself. When information is transmitted through entangled systems, the mathematical structure that describes this process looks identical to the equations governing a particle moving through a wormhole. What we call travel may simply be the re-expression of correlation across space. This insight provides a new way to think about one of physics' most persistent puzzles: how black holes process and release information. The Hawking radiation emitted by black holes appears random, yet if information were truly lost, it would violate the fundamental principles of quantum theory. The wormhole framework offers a potential reconciliation. The entanglement between particles falling into a black hole and the radiation escaping from it can be described as a network of wormholes linking the inside and the outside. Information does not vanish. It is redistributed across space-time through these invisible connections. In a sense, the universe itself ensures that information remains conserved by weaving it into geometry. Such ideas remain theoretical, but their internal consistency is striking. They imply that the same quantum processes responsible for the stability of atoms and the behavior of light may also shape the largest structures of the cosmos. Wormholes, once speculative curiosities, become symbols of the universe's self-organizing intelligence. They demonstrate that space-time is not a fixed background, but a dynamic expression of quantum relationships. Still, there are limits to how far this analogy can be taken. The wormholes described by physicists like Jafferis and Susskind are traversable only for extremely small amounts of information and exist for infinitesimal durations. They cannot serve as cosmic shortcuts or time machines. Moreover, the negative energy required to sustain them has never been observed in quantities large enough to affect macroscopic geometry. In all known physics, the conditions necessary for a human-scale wormhole remain impossible to achieve. Theoretical models, however, continue to explore the boundaries of possibility, testing the idea that gravity, space-time, and quantum information are merely different expressions of the same underlying reality. One of the most compelling philosophical consequences of this research is the redefinition of distance itself. If information can be shared through entanglement that spans light years, and if this sharing can be equivalently described as a geometric connection, then far apart may not mean what it seems. Two systems entangled at the quantum level may, in a deeper sense, occupy the same informational space. The wormhole is then a map of that hidden proximity, showing how the universe connects things not by moving them closer, but by eliminating the need for space between them. This perspective has begun to influence cosmology as well. Some models suggest that the large-scale structure of the universe, the cosmic web of galaxies, might reflect patterns of entanglement in the early universe. The expansion of space could be interpreted as the unfolding of these connections, while gravitational attraction might represent their tightening. Even the vacuum of space, filled with fluctuating quantum fields, may harbor a dense network of microscopic wormholes linking distant regions of the cosmos. Though these wormholes are unimaginably small, they could underpin the coherence of the universe, ensuring that information and causality remain consistent across vast scales. If these ideas are correct, then communication through a wormhole is not science fiction, but an expression of how reality itself communicates. The universe, viewed through the lens of quantum gravity, is a vast information network in which geometry and entanglement are interchangeable. Every exchange of data, every correlation between distant events is a whisper across the fabric of space-time, a form of transmission that needs no motion. In this light, the question, can information really pass through a wormhole, becomes almost self-referential. Information does not simply pass through a wormhole, it creates the wormhole. The act of correlation shapes geometry. The very concept of a path from one point to another depends on the flow of information that defines those points in the first place. Space and time, in this view, are emergent conveniences, arising from a more fundamental language of informational relationships. As speculative as these notions sound, they are built upon the most rigorously tested foundations of modern physics: quantum mechanics, general relativity, and thermodynamics. What remains uncertain is how far these connections extend and whether we will ever detect direct signatures of quantum wormholes in nature. For now, they remain bridges in theory, guiding us toward a deeper synthesis of the laws that govern the cosmos. In the stillness of night, one might find a quiet resonance in these ideas. The thought that the universe is bound together not by force, but by information, lends a kind of elegance to existence. The same principle that links photons across billions of light years may also connect hearts and minds across the smaller distances of human experience. Nothing is ever truly isolated. Every thought, every particle, every star participates in the same unfolding web of connection. As you let go of the day, imagine that web stretching across the darkness. An infinite lattice of bridges made not of matter, but of understanding. Perhaps every moment of awareness is itself a tiny wormhole, a portal through which the universe knows itself. Through you, the cosmos continues its quiet conversation, information flowing without travel, geometry breathing without motion. Chapter 10. Entanglement, Connection, and the Nature of Reality. Throughout the history of physics, humanity's understanding of the universe has evolved from the motion of objects to the structure of space, and finally to the flow of information. Quantum mechanics, which began as a theory to explain the behavior of atoms and light, has gradually revealed something far deeper, that connection, not separation, may be the fundamental feature of reality. Entanglement, once viewed as a curious side effect of quantum theory, has emerged as the central thread weaving together matter, energy, space, and time. What began as Einstein's spooky action at a distance has become the foundation upon which physicists now attempt to rebuild the entire picture of existence. To grasp how this transformation occurred, one must recall what entanglement really means. It is not a mystical bond, but a precise mathematical condition. When two or more quantum systems interact, their combined state can no longer be described independently. Their properties become correlated in ways that persist even when they are far apart. Measurement on one system affects the statistical description of the other, not through any signal, but through the shared structure of their wave function. Experiments across decades, from photons and electrons to massive molecules, have confirmed that entanglement is real, robust, and universal. It is not limited to exotic laboratory conditions. It operates within every atom, every interaction, every exchange of energy in the cosmos. As quantum theory matured, physicists began to realize that entanglement is not just a feature of particles, but the very language of physical law. In the quantum field theories that describe all known forces except gravity, every particle is an excitation of a field that extends through all space. When these fields interact, they become entangled, creating the complex network of correlations that defines matter and radiation. The classical world emerges from this network when decoherence, interaction with the environment, suppresses quantum interference, leaving behind the appearance of separate, stable objects. Yet beneath that apparent separateness lies the continuous entanglement of everything with everything else. The boundary between systems is a practical convenience, not a fundamental truth. The past several decades have deepened this understanding through unexpected connections between entanglement, information, and geometry. The holographic principle and the DSCFT correspondence show that the structure of spacetime itself may be encoded in patterns of quantum entanglement. The strength of correlation between regions of a quantum system can determine the distance between them in the emergent geometry. In this sense, space is not a stage where physics happens. It is the visible shape of invisible relationships. Gravity, too, may arise from the collective behavior of entangled quantum states, with the curvature of spacetime reflecting the distribution of information. This vision of the universe as a web of entanglement unites the smallest and largest scales of nature. At the microscopic level, quantum computers now manipulate entangled qubits to perform calculations that would take classical machines longer than the lifetime of the cosmos. At the cosmic scale, the quantum fluctuations that once rippled through the infant universe left imprints in the cosmic microwave background that seeded the formation of galaxies. Entanglement thus links the birth of the universe to the workings of technology in our hands, a continuity that erases the imagined divide between the human and the cosmic. What makes this realization so profound is that it forces a reconsideration of what we mean by reality. The classical worldview assumes that objects possess properties whether or not they are observed. Quantum mechanics dissolves that assumption. Properties are not absolute, they are contextual, emerging only through interaction. The universe, therefore, is not composed of things, but of relationships. Observation does not reveal a pre-existing world. It participates in its creation. This interpretation, supported by decades of experimental verification, does not make reality subjective, but relational. Each measurement, each moment of awareness defines a slice of the grand quantum whole, an intersection of correlations extending across time and space. Such a worldview invites both scientific and philosophical reflection. If entanglement defines existence, then isolation is an illusion. Every system, from the smallest particle to the largest galaxy, is part of an uninterrupted continuum of information exchange. The separations we perceive are convenient approximations drawn by limited perspective. Even the flow of time might emerge from entanglement. Some interpretations of quantum gravity propose that temporal order arises from the growth of correlations among systems, as information spreads and becomes shared. Time, in this sense, is the unfolding of entanglement, the universe remembering itself. Physicists exploring these ideas have found that entanglement is not merely descriptive, it is generative. It creates structure, defines energy, and shapes the stability of matter. The fabric of space may be woven from quantum connections, but the texture of reality as we know it, solid, tangible, and continuous, emerges from the collective harmony of countless entangled interactions. The world we experience is the surface of an ocean, whose depths are invisible but not absent. At the same time, entanglement presents challenges to our deepest intuitions. It denies locality, defies reductionism, and demands that knowledge itself be seen as a physical quantity. Information cannot be separated from the physical systems that carry it. When we observe the universe, we are not detached spectators, but participants in its informational flow. Every observation changes the distribution of correlations, subtly altering the world we study. The old boundary between observer and observed, long upheld since Newton's time, fades into a continuous exchange of information, a cosmic dialogue that never stops. This shift in perspective has consequences not only for physics, but for the philosophy of being. The classical notion of objectivity, of a universe that exists wholly independent of our participation, gives way to a more subtle realism. The universe does exist independently, but what we call reality is our interaction with it, mediated by entanglement. We are not outside the system, we are inside the wave function. The act of knowing is itself a quantum process, part of the same entangled web that defines stars, atoms, and thought. In this view, consciousness does not violate physics, it reflects it. Awareness can be seen as the brain's way of integrating vast flows of information, reducing quantum complexity into a coherent experience. While science has not established a direct link between consciousness and quantum mechanics, the parallels are intriguing. Both involve the transformation of uncertainty into meaning, the collapse of many possibilities into one experienced reality. Whether the mind is quantum or not, it operates within the same universe whose deepest law is connection. Modern experiments continue to push these boundaries. Quantum networks entangle photons between orbiting satellites and ground stations. Superconducting qubits maintain coherence long enough to demonstrate the logic of quantum algorithms. Even biological systems show hints of quantum coherence in processes like photosynthesis, suggesting that nature has been using quantum effects long before humans learned to describe them. Each discovery reinforces the same idea. Entanglement is not rare, it is universal. The cosmos functions as a single computational structure, continuously processing information through the language of quantum correlation. Yet amid all the equations and experiments, a quiet question remains. Why does anything exist at all? If the universe is a vast informational system, who or what defines its boundaries? Perhaps there are none. Perhaps existence is simply what happens when information becomes self-referential, when the universe observes itself through the countless lenses of its own structures. In that sense, every particle, every life form, every mind is a point of reflection in the cosmic mirror. Entanglement ensures that each reflection contains the whole. As the night deepens and thought slows, consider this. The same physical principle that binds two photons across the void also binds you to the universe that created you. Every atom in your body was once part of a star, and before that, part of a quantum field stretching across space. You are not separate from the cosmos. You are one of its expressions. The connections that sustain you are not abstractions, but physical truths written into the structure of existence. So let the day fade, and let the stillness return. The universe continues its silent computation, threads of entanglement vibrating through every scale of being. Reality is not a collection of things, but a harmony of relationships, an infinite web of cause and correlation, chance and meaning. And within that web, you are both observer and participant, an ephemeral node in the eternal network of connection, where nothing is ever truly alone. Thank you for joining me, my friend. If your eyes are still open, there's another journey waiting, just there on the screen. And if you're already drifting off, sweet dreams among the stars.